All right, so I'm Jack Plantz from Telluride High School, and this summer I got to go to the Stanford Linear Accelerator Center in Menlo Park, California, and work with electrons and do particle physics. Let's go. There we go. All right, so this is the SLAC accelerator complex. It's 2 miles long, and it can accelerate particles up to 0.99999 the speed of light, which is 6 nines. So we can get them going really fast. And it was built in the 60s for high energy physics and discovering new particles. They won 3 Nobel Prizes out of research out of this center, including discovering quarks inside protons and neutrons. So it was really incredible to work here. And so here's one of the experimental halls. I'll come back to this. So I got to work with my mentors, Dr. Tor Robenheimer and Juhao Wu. Tor, he's an awesome climber. Actually, the first time I emailed him, he was out climbing in Thailand, so it took a long time for him to email back. But he took me out to this climbing gym every other day, and it was super fun to get out of the lab and talk with him about climbing problems rather than physics problems. But he was actually leading the design of a new free electron laser at SLAC, and so I couldn't help him with his work. So I worked on a research team with Juhao Wu, with several college interns and grad students. Oh. Okay, there we go. All right, so here was what I worked on is the linear coherent light source, which is since a lot of the elementary physics has moved over to CERN in Switzerland, they've repurposed the accelerator into this free electron laser. So basically what that is these electrons come into this undulator hall going very close to the speed of light, and these magnets move their path up and down. And when they do that, it releases light at the wavelength they do that. And so these magnets are spaced about this far apart, but because of special relativity, the space is actually dilated, so it's about 400 million times closer together. So the wavelength you actually get is the wavelength of an atom. And so you have these incredibly high frequency waves that you can use for imaging. That is the wrong way. Okay. Okay. Yeah. So you can. So you can send these this beam through like cancer cells and complex proteins, and you can measure their diffractions and create these 3D models of the structure of elements and all these complex proteins. And so it's hugely valuable for cancer research and material science and anything where you need to know really specific chemical formulas of things. And because it's so bright, it's actually brighter than the sun, but in X-rays. You can do these with basically a very fast shutter speed. So you can take pictures of like chemical reactions as they happen, and you can watch the vibrations of hydrogen atoms, and it's crazy all the stuff you can do. So I was primarily working on making this beam more useful for research, and so that entails making it more coherent, so more in the same wavelength and in the same phase. And so what you have is like about 1 billion electrons are going through this with each pulse, and so they all interfere with each other. And so ideally you'd like the photons that each electron emits to stimulate the ones in front of it and make them all emit exactly the same in exactly the same time. But the light is actually not going very much faster than the actual electrons, so it doesn't even catch up to hardly any of them at all. So you can delay these electrons relative to the light and move them forward and have them catch up to the light that they would never normally get to. And so we had 2 of these 4 magnet chicanes that just take it on a detour away from the beam, and we were experimenting with different values to figure out what's the most efficient and what makes us or gives us the most coherence. And so you can't actually go in the beam because it's radioactive and it would kill you. So I was in this office doing a lot of math and a lot of code. I actually had my dad mail me my calc minder so I could remember how to do all these infinite series and crazy stuff that I never thought was actually real math that you'd use for something. Uh, and so, and beam time is incredibly hard to get. They run the beam 24 hours a day and 7 days a week, and they still have to turn down like 70% of the applications they get. So we ran a bunch of simulations on a computer. And so I had to interpret all the data from that with Python, which is the same thing that Elliot used, but I had no idea how to use it. So I had to learn how to do that. And so here are the graphs I made using Python, which was really awesome, and they make me happy because they were really hard to make. And so they're all showing different undulator configurations and different variables and outputs. But they show the spectrum, and the height is how powerful it is, and the width is the frequency it's in. So ideally, you'd like it all in the same frequency and a huge peak. So this graph right here, the red line is our improvements, and the blue line is the standard configuration that they've been using. So it's about twice as powerful and twice as coherent. So in theory, it should work really well. And we got to test this on the actual beam. We got scheduled from 11 at night till 5 in the morning. And we were like, it was really huge that we got this beam time, so we had to go in there and use the time as much as we could. And so I got really tired. It was 2 in the morning, and we were still trying to get the beam to the specifications that we wanted it to be. We ended up getting to take data at around 3 a.m., and so I think it took us about halfway through the data we wanted to collect, so they'll get another beam window. I think they have had one, actually, and now they're working on analyzing the results. Also, while I was there, I got to do a bunch of stuff outside the lab. I hung out with all these college interns, and we went down to Big Sur and went surfing and hiking, and we had bike races around Stanford campus. And then I also got to go to Outside Lands Music Festival, which was incredible, and it was ridiculous. There was about 200,000 people there every day, so like, way more than Telluride. And it was really fun. I missed the last train home at midnight in San Francisco and had to find my way home. That was fun. And so my message to future Pinhead interns would be to obviously work hard and get the most you can possibly get out of your internship, but also have fun. And I think I figured out most of the things while I was climbing or hanging out with the interns, and not while I was struggling in the lab with the code. And so definitely, if you have the chance to race spinny chairs next to a $1 billion electron laser, go for it. Just don't run into it. And so I'd like to give a huge thank you to Pinhead and everyone who's donated for making this awesome experience possible. And also to the Gershenbergs, who was the family I stayed with, and to Tor and Juhao for being so incredible and explaining everything about the electron laser to me.